Hello and welcome to this lecture. My name is Mira Kuchibuza Marcel, and I'm the founder and the director of the Pan African Citizen Science Laboratory. So, today we are going to be learning about the cosmic messenger electromagnetic waves. Okay, the cosmic messenger electromagnetic waves. So remember in my last lecture, I introduced the cosmic messenger, okay, and I also gave a history of the discovery of the four different kinds of cosmic messengers we have, and I also explained why are multiple messengers necessary, why they are necessary. So, and I promise you that in my subsequent lectures, I'm going to be focusing on each of those cosmic messengers. And that is why I'm treating electromagnetic wave first. So, as a part of table of content, so I'm going to be introducing electromagnetic waves. I'll discuss the properties of electromagnetic waves, and I will talk about the electromagnetic spectrum in astronomy, and then the telescopes used for different wavelengths of the electromagnetic waves. Now, talk about the advantages and the limitations of the electromagnetic waves. So, by the way, this lecture is sponsored by the Free Astro Science Group. So, now, introduction to electromagnetic waves. So, electromagnetic waves or EM waves are oscillating electric and magnetic fields that travel through space, carrying energy from one place to another. I said electromagnetic waves are oscillating electric and magnetic fields that travel through space, carrying energy from one place to another. So that sounds familiar. That is like the definition of a wave, ordinarily, like the definition of an ordinary wave. Okay, because waves they carry energy, okay, from one place to another. But for this one, it is different. I'm going to see why. So, electromagnetic waves travel perpendicular to each other. I mean, the electric field and the magnetic field, they are perpendicular, that means they are 90 degrees in their oscillation. And they are also perpendicular. Both of them are equally perpendicular to the direction of travel. And I thought transverse waves. Okay, so if you look at this diagram, you can see the horizontal direction here. Here it is the axis. It is the direction of the magnetic waves. So that is B. So up vertical is the direction of the oscillation of the electric field. So you can see that they are perpendicular to each other and then to the direction of the wave. The wave is moving in the x direction. You can see that the wave is moving in the x direction while the B is oscillating in the vertical direction and the magnetic field is oscillating in the horizontal direction. So I hope that makes a lot of sense. And there are what? Transverse waves, because transverse waves are waves that travel perpendicular to the direction of motion. Okay? So now the existence of these electromagnetic waves was predicted by the Scottish theoretical physicist James Clerk Maxwell in the 1960s through his four famous equations, which unified electricity and magnetism into a single theory. And those are the equations. And what does this equation mean? Okay, if you look at it as an amateur, they look so scary. But I'm going to break it down for you. They are very simple. The first equation is called Gauss law. So it says that if you place a charge, it is going to diverge across all space. It is going to be what? Diverge. So if you place a positive charge, it's going to diverge out. It's going to be emanating out. If you place a negative charge like electron, it's going to be moving in. Charge are going to be moving in. And it also means that we also have this idea of electric uh, monopole. We have electric monopole. Then, because you can separate the two. Then we have um, Gauss law for magnetic field. If you for the magnetic field, if you get a magnet and you split it into two, let's just say you get a ball magnet and you split it into two, you will discover that as you split it into two, you just created two magnets. So even if you continue splitting it and splitting it and splitting it, it is not possible to get a single magnetic north or magnetic south. You can't separate the two. Okay, so you're always going to have a magnetic dipole. Okay, so that is the essence of this equation. It means the divergence of the magnetic field is zero because we don't have a magnetic monopole. It is always a magnetic dipole. So those two are Gauss law for electric field and for magnetic field. Now, how about electricity? How about this equation? The third equation, it says that the change of electric field is going to give you a change in the magnetic field. Okay? A change in the electric field is going to give you a change in magnetic field. And the fourth equation is just the the reverse, I mean the vice versa. It says change of magnetic field is going to also going to give you electric field. I'm going to show you where this thing applies. Okay, I'm going to show you where it applies, and that is him, James Clerk Maxwell. So with this equation, he derived all kinds of things. First of all, he was able to theoretically predict the speed of light. And all of these things are the components of light because this one has to do with statics, but this one has to be with a changing system. You're going to see what I mean by that. So in 1988, after his theoretical work, um, Henry Hertz experimentally used this tool, this setup here, to confirm the existence of electromagnetic waves. He first of all discovered the existence of radio waves, and subsequently other scientists discovered others, all the way to gamma rays. Okay, but he was the first person that experimentally demonstrated the existence of these electromagnetic waves. So examples of these electromagnetic waves include um, we have radio waves, we have microwaves, and we have infrared radiation, and we have visible light, we have ultraviolet radiation, we have X-rays, we have gamma rays. Now, although they may appear different, they are fundamentally the same phenomena. I will explain what I mean by that. They differ only in their wavelength, frequency, and energy. So here this is a diagram showing the electromagnetic spectrum. We have radio waves, microwave, infrared, we have ultraviolet, we have visible light here, sorry, we have ultraviolet, we have X-rays, we have gamma rays, and so forth and so forth. Now, remember what I talked about Maxwell's equation? I said a change in electric field gives magnetic field, and a change in magnetic field gives electric field. And I also said that this is all about static electricity, and this is where electricity is moving. So now, remember I told you about a charge kept in a place or moving at a constant speed. Because in physics, any object moving at a constant speed is the same as though it is stationary. Okay. Now, what if you move the charge vigorously? Now let me use this diagram as an example. Assuming this is an antenna, okay. Let me just use this vertical direction. Okay, this is an antenna. Okay, now antenna, what they do is that they help electrons or charged particles to move very vigorously. Okay, so if you move these charged particles to a very high speed, okay, to a very high speed, charged particles have electric fields around them. Okay, they are radially pointed outwards. So when you vigorously move them, if you accelerate them, you see that the field the field around them is going to bend, and that is a form of a change in the field. That's an acceleration. If you accelerate them, they're going to bend, and that bending is exactly what we talk about, the change in electric field. And what will happen, it will give rise to magnetic field. That is why, as this magnetic field is being produced, it is going up, it is immediately producing a magnetic field. I mean, as this electric field is going up or down, it is immediately creating our magnetic field. And magnetic field is creating an electric field, and the two are moving out from the source. Okay, they are moving out of the source, as you can see what is going on in the picture. So that's exactly what I wanted to demonstrate here. So now, so what is the difference between radio waves, microwaves, and all the way to gamma rays? So the difference is just in the energy moving the charge. If the energy is not much, the charge will move less. Okay, the charge will move less. The electric charge, I mean the electrons in the wire, will move less. If the energy is high, they will move faster, so producing more of these waves. So that is why we have radio waves, and we have gamma rays. They are just basically electromagnetic waves. It's just that they are different in their different in their wavelength, their frequency, and in their energy. So unlike sound waves, sound waves are mechanical waves because they require material medium for their propagation. So look at this demonstration here. You see that these are mechanical waves like sound. It requires a material medium. So for instance, something like a sound requires air, requires and also requires liquid and solid to propagate. But for electromagnetic waves, they do not. Electromagnetic waves do not require material medium for its propagation. They move in the vacuum of space. Okay, so and that is what makes them ideal candidates or ideal messengers for distant celestial objects because they don't require that. If you look at this picture, you see that sound moves faster with solid, followed by liquid, and followed by gas. And this example of this gas is air. That means sound moves faster in solid surfaces. So take note of that. Now let us go into the properties of electromagnetic waves. These are just the same thing with the properties of all waves, but particularly for electromagnetic waves. So number one property is wavelength. The wavelength is simply the the distance a full cycle of a wave moves. Because a wave is a full cycle. Okay. For instance, if you start from here, let's just say we start from here and you move from here to here, that is half cycle. That this is another half cycle, which is complete cycle. So this is one wavelength. From here to here is one wavelength. If you do the same process again, you have two wavelengths of units. Okay. So depending on what you're measuring, it's a distance. So it is measured in the units of distance like meters or centimeters. But for SI units, we use meters. So it is just the the distance moved by a full cycle of a wave. Okay. So in physics, we say the distance traveled between two successive crests. Crest is the top of the wave, or the troughs, which is the bottom of the waves. Okay. So now for gamma rays have the shortest wavelengths. Okay. Why radio waves have the longest wavelengths? So take note of that. So here is a picture. I've shown you this picture before of the electromagnetic spectrum. So we have the radio waves. You see how long they are, Microwave, they get shorter and shorter as you move to the gamma rays. Okay, so if we take the visible spectrum, our visible spectrum, to be a center of reference, you will see that all the wavelengths that are towards the left are referred as longer wavelengths, and all the wavelengths towards the right are referred to as shorter wavelengths. Now, how about the frequency? Frequency simply means how many cycles of this wave is produced per second. How many cycles of this wave is produced per second? How many cycles per second? So that means, so look at this demonstration here. So you see, it was sluggish before, but now it increased. So how many waves it could produce per per second? So that is exactly what we refer to as the frequency. So if you want to imagine it, imagine your fan. So if you put it at some level, it will move in slowly. If you put it at the highest level, it will move very fast. So just imagine it like that. Okay. So so different frequencies correspond to different regions of the electromagnetic spectrum. So so for the electromagnetic spectrum, gamma rays have the highest frequency, while radio waves have the lowest frequency. So here, like there's a reversal in the wavelengths, gamma rays have the shortest frequency, but here they have the highest. Sorry, here gamma rays have the shortest wavelength, but here they have the highest frequency. So there's a balance. So if there is increase in one, there's decrease in the other. So the same thing with the radio wave, they have the longest wavelength, and here they have the lowest frequency. So that's a balance. And you're going to see why that balance is important. So another property of a wave is energy. Okay, waves carry energy. Okay, so now to understand this idea of energy of a wave, I want you to imagine a wave as as a particle. Imagine it as a particle like you have a particle like stone, you have your object around you. Just pick one of them. Just pick a sand or a single grain of rice. So particles, right? So imagine light like that. I was talking about waves, but just for the sake of this, we have we actually have a theory on that. We have called it wave particle duality because for in the quantum level, in the smallest of things, in the world of the small things, okay, this there is change in behavior. Sometimes they behave like particles, sometimes they behave like waves. So for the sake of to understand energy very well, I want you to imagine them as particles. Now, if you imagine them as particles, a particle of electromagnetic wave is called a photon. Okay? So now that photon carry energy. I hope it is making sense now. They carry energy because they are always in motion. They carry energy, and the equation of deriving the energy is given by this. So it is energy equals to the Planck's constant times frequency, or if you want to use wavelength, you can say energy equals to the Planck's constant times the speed of light over wavelength. Okay, so this is applied in photoelectric effect, or simply put, your solar panels, when it gets hit by sun, okay, the electrons move. Okay, so they eject electrons from the surfaces of these solar panels. So that's exactly how it works. We call it photoelectric effect. So if you do that with energetic particles like gamma rays, if you do that with gamma rays, you see that gamma rays are able to eject the these particles very easy. Okay, but if you try that with radio waves, they are not. So you see that gamma rays have the highest energy, while radio waves have the lowest energy. Okay, so this is how you can imagine. So this is exactly what is happening here. You can imagine it in the atomic level. Okay, this is the orbit of an atom. okay, with electrons around it. So when gamma rays hit it, they eject the electrons from the surface. And that electron, the movement, is what we call electricity. Okay? So now we've discussed that we have to discuss wavelength, frequency, then energy, and then speed of light c. Speed of light c. Again, all electromagnetic waves are called light. Know that all so in our normal daily activities, whenever we hear light, we think many things. We think about electricity, we think about visible light, okay, we think about many things. But in physics, light, it is physics that defines light, and light is simply all those electromagnetic waves from radio waves to gamma rays. So, and I said they are light, and they travel through the vacuum of space in the speed of light. Okay, they travel through the vacuum of space in the speed of light. So here is the formula for the formula for waves in general. So if you for all of these frequencies and wavelength that we just all these gamma rays, if you get their frequencies and their wavelength, okay, if you multiply them, they're going to give you this number called the speed of light. It's a constant number, 3 times 10 raised to the power 8 meters per second, and the speed of light is constant. Okay, so what I mean by this is if you want to arrange a race for radio waves all the way to gamma rays, and you want to know which one will faster. If you do that, you discover all of them are going at the same speed. No one will be first or last. If you, I mean, all if conditions are equal across the three, they all travel at the same speed. So, but someone may ask, I thought you said gamma rays have the highest energy, so they should be the first. They should be faster. No. Remember what I told you here? Look at the formula for waves. Formula for wave is frequency times wavelength. And remember that I told you about wavelength and frequency. For gamma rays, you see that as it is as it possesses the highest frequency, it possesses the lowest wavelength. So that we always cancel out. The effect of this one will cancel the other one so that they will maintain the same speed. So they adjust the wavelength and the frequency adjust to maintain the speed of light. You know, when I first heard it, it was very hard for me to believe, but now I believe it. Okay, so so I said all electromagnetic waves move at the same speed, c. And why do we use c? Why didn't we use v? So the c was chosen because light is a special kind of thing in physics. Light, the c means celeritas. It's a Latin word for swiftness or speed. So we use it because it is a very important constant in physics and in cosmology and astrophysics. So we use C, and that's the constant value there. And this value is only applicable in vacuum, please, not in mediums. Okay, when it enters medium, that is why we have diffraction. We have these rainbow colors. Okay, I'm not talking about that. So this is different. This is for vacuum. So one more important thing I want you to know about photons or light is that photons, like you can see them here, they do not have mass. They do not have mass. Okay, they are massless particle, and they that's why they move very fast. In fact, they are the fastest thing in the universe. The fastest thing in the universe are this speed of light. Light is the fastest speed in the universe in a vacuum. Okay, so nothing is faster than the speed of light. Nothing. So it places an upper limit. That is why I told you light is very special. So so light is so fast that within 1 second it can go around Earth over 7 times. And even from our sun is about 150 kilometers away from us, from Earth. It takes as far away as the sun is. It takes about 8 minutes for the light from the sun to reach us here. So that means if something happens to the radiation of the sun, we're not going to know until 8 minutes later. How about the nearest star system? It takes about 4 years for light to travel from those places to us. So here is the table that contains all the electromagnetic spectrum, all the electromagnetic spectrum. Okay, so we have radio waves. Radio waves are their wavelength is not a single number. Not just radio, all of the electromagnetic spectrum. Their wavelengths and frequencies are not a single number. Inside, we call it electromagnetic spectrum. Okay, but inside each of them, we also have their individual spectrum because their wavelengths and frequencies are not a single number. So for wavelength, for wavelength of radio waves, they are anything above 1 meter, and they can reach up to 100 kilometers. There's no upper limit. There's no upper limit. They can be so big. And this 100,000 already is much bigger than Earth. So those kind of wavelengths come from space. So the frequency is um, less than 3 megahertz down to 3 hertz. Hertz is the unit for frequency. So microwaves are upper radio waves. I mean, more energetic radio waves. Their wavelength range between 1 millimeter to 1 meter, and their frequency range between 300 megahertz to 300 gigahertz. For infrared, they are between 700 nanometer to 1 millimeter, and the frequency range between 300 gigahertz to 430 uh, terahertz. Okay, I think that's terahertz. Then for visible light, our own one we are sensitive, our eyes are sensitive to. Okay, we have it between 400 nanometers to 7 nanometers, and the frequency range between 430 terahertz to 790 terahertz. How about ultraviolet radiation? They range between 100 nanometer to 400, sorry, 10 nanometer to 400 nanometer. They range between 790 terahertz uh, to 30 petahertz. Then we have X-rays between 0.01 nanometer to 10 nanometer. They range between 30 petahertz to 30 exahertz. We have gamma rays, anything less than, there's no lower number, but anything less than 0.01 nanometer. And the frequency is anything above 30 um, exahertz. So the same thing for radio waves, there is no upper limits for radio waves, and also there's no lower limits for gamma rays. So they can get, their wavelength can get as small as possible. Okay, so now let us discuss the application of electromagnetic spectrum in astronomy. But before I say that, I want to I want to tell you that everything in the universe emits a form of electromagnetic waves. Even the ice in your freezer emits electromagnetic waves. It might be emitting thermal, I mean, um, infrared. It might be emitting radio. It might be emitting um, microwaves. It might be emitting visible light. Okay. In fact, it's emitting visible light. That's why you can see it. When you open your refrigerator, you can see it because it is reflecting visible light. The process of reflection in the atomic level. So I don't want to go there. But why do I say that? Why do I say ice is emitting something? It's because it is not possible to achieve an absolute zero. It is a quantum mechanics problem. It is not possible. So as far as an object is exists, it is emitting something. Okay, it is not possible to have absolute zero Kelvin. It must have minus 273, you know, or 0.000000001 Kelvin. So, and what is the definition of heat, or what is the definition of of what causes what what causes distance? What causes them? It's because of the movement of electrons. When these electrons are moving in their shell, there's an acceleration. And I told you they have charges around them. There's an acceleration. So as they're moving around their shell, there's a change in electric field, and that will give the magnetic field. So they always radiating something. So for you to bring the electrons orbiting an atom to a complete halt means you have achieved zero Kelvin, and we have not achieved that. So everything in the universe is emitting something. I want you to bear that at the back of your mind. So now let us see how these electromagnetic waves apply to astronomy. So for radio waves and microwaves, I'm going to combine them because in engineering and in most part of physics we combine them because microwave is just simply higher frequency radio waves. So so the astronomical importance of radio and microwave is that it helps us in mapping the Milky Way. This is the map of the Milky Way. This is the Milky Way. It helps to map the Milky Way because the gas and dust and everything is emitting something that emitting radio waves, microwaves. Okay. Then in detecting neutral hydrogen in the universe, neutral hydrogen. Universe is made up of about 90% of hydrogen and helium. Remember my last lecture, 90% of hydrogen and helium. Okay. Some are existing as neutral hydrogen, some are existing as ionized hydrogen, while some are excited, or should I say, I'm sorry, molecular hydrogen, like molecules, like two hydrogen combining together. So now, for those that are existing as excited or ionized hydrogen, when they deionize or when they de-excite, when they go back to their orbit, they give out energy. They remove the energy they are carrying to be able to go down to the lower energy level. Okay, so that line is well known. We call it 21 centimeter hydrogen line. So it helps us to take the detect due to hydrogen and the prevalence in the universe. We use radio waves and we use radio waves for for searching for pulsars, and also we use it to search for intelligent lives. We believe that if there is an intelligent life in the universe, they might be sending us radio signals, just like we are sending the radio signal. We are doing that to them. So that we use it for searching for intelligent lives in the universe, radio waves. So active galaxies give out radio waves, and then we have the cosmic microwave background radiation. It is a radiation that was emitted during the first stage of the universe. It's a long process. Maybe I'll talk about that later. So we call it the cosmic microwave background radiation. It is a microwave. So this is the shape of the universe. It is used to study. It is used in cosmology. Then how about infrared radiation? Infrared, what we call infrared is the heat that you feel. What you feel as heat or high temperature is called infrared. Okay. What makes you uncomfortable? You want AC, I mean air conditioner, you want fresh air, is actually infrared. And it is emitted by relatively all cool objects. But in astronomy, their sources include dust in stars in dust clouds. So look at this picture of the Eagle Nebulae. This is the Eagle Nebulae. Okay, this is the Eagle Nebulae in the optical spectrum. You can barely see stars there, only a couple of. But if you view the Eagle Nebulae in the infrared, you're going to see lots of stars. So what happened? It means that they are emitting most of their energy in the infrared spectrum. So you can see that. Then how about forming stars in clouds? Just exactly, almost like the other one. Forming stars, this cloud cover some there are lots of cloud in heaven. So they cover they cover star formation regions, and we don't know there are stars there until something happens. But these stars emit. We can see that we can still see them through infrared. Then we have brown dwarfs. Brown dwarfs are stars that we call them failed stars. They failed to acquire enough mass to ignite nuclear fusion at the center. So they are only emitting heat, infrared radiation. So we see them, even rock planets too. So so planets that are orbiting their stars, Okay, we use we use infrared to detect them. So if you cover the star here, you can see the planets orbiting around it. You can even use this for our sun to detect comets. So they emit infrared. How about cool stars? So and so on and so forth. Then we have visible light. Visible light is the only part of the electromagnetic spectrum detectable by the human eyes. It has been used by ancient people with our eyes to see the universe and to document some things that happened in the time past. They used their eyes before the invention of telescope by Galileo Galilei. So, so most traditional astronomy relied entirely on the visible light and use it to review and to see stars in the heavens. You can use it to see stars. You can even use optical telescopes to see stars, in the bigger form. You can use it to see galaxies. You can use it to see beautiful nebulae. They're all in the visible spectrum. You can even use it to see planets in our solar system at night. You can see them. You can see the moon. So, these things are very visible in our night sky across the world, not in Europe and not in America, across the world. Even if you're in Africa, you can see them. So how about star clusters? They all emit in the visible spectrum. Then how about the ultraviolet spectrum? Ultraviolet radiation originate from extremely hot object. Examples include young massive stars, like you have it in the Pleiades. They are in the ultraviolet spectrum. They are very, very, very bright. That they emit most of the energy in the ultraviolet. And if you look at these, if you look around them, you see some kind of clouds or kind of nebulae. They're looking blue. And the reason why they are looking blue is because of the energy. The energy from these stars, excites or ionizes the dust around them. So when they deionize, when they fall back to the atoms, they emit light, and that is why we can see them in looking that blue. So that happens even with nebulae that we talked about here. So I'll talk about that here. So how about hot white dwarfs? What are white dwarfs to start with? White dwarfs are remnants of stars after main sequence. So we have three classes. We have white dwarfs, we have neutron stars, we have black holes. Remember, that's the remnant of stars. So white dwarfs is at the lower end for low mass stars. Okay. So when they are dying, they eject their surface into planetary nebulae. This beautiful. So, but if you look at the center, you see a dot, a bright dot at the center. Those are white dwarfs. They are just the size of Earth. They are just very tiny and very energetic. They emit in youth ultraviolet, and the same process I just described here happens here. So because of the high energy, they excite and ionize the particles around them, and when they de-excite, they glow in these beautiful colors. So we have also regions of active star formations also give rise to ultraviolet radiations. How about X-rays? X-rays are produced by extremely energetic environments, like we have event horizon of black holes. Event horizon of black holes. We have neutron stars. You have a system of binary stars. One is a main sequence star, very massive, and you have a neutron star. And because of gravitational imbalance, this neutron star will begin to steal matter from this bigger star, the main sequence star. And as the matter is falling, they are falling with a great speed, and that energy is transmitted as X-ray. Energy can be converted from one form to another. So the potential energy, potential energy converts to kinetic energy. The kinetic energy of the infalling matter converts to X-rays, energetic energy. So that would happen. So we have supernova remnants like this. Supernova remnants, they are in X-rays. And how about hot gas in galaxy clusters? So, you know, X-rays allow astronomers to study matter falling inside black holes and other high energy processes. So, how about gamma rays? Gamma rays reveal the most energetic events in the universe. They are produced by gamma ray bursts. You can see them here, gamma ray bursts from pulsars, gamma rays. Okay, then we have supernova explosions, gamma rays, and how about active galactic galactic nuclei, AGN, and then matter falling inside black holes. They emit gamma rays. So let me give you a summary of everything I've just talked about the electromagnetic spectrum in astronomy. So for I'm gonna call astronomical object and call what they emit mostly for planets. For planets, they emit visible light and infrared. For stars, they emit visible light UV and infrared. For brown dwarfs, they emit infrared. For nebulae, they emit visible light and radio waves. For molecular clouds, they emit radio waves and infrared. For pulsars, they emit radio, X-rays, and gamma rays. For black holes, they emit X-rays, gamma rays, and radio waves. And for galaxies, they emit radio to gamma rays. For active galactic nuclei, AGN, they emit radio waves, X-rays, gamma rays. So for cosmic microwave background, they emit microwave. So you see most. So for each of these celestial objects, they emit one or two or three of these electromagnetic waves. Now let's talk about the telescopes used for different wavelengths. I'm going to focus on the most popular ones. So for radio waves, the telescopes we use to detect radio waves are called radio telescopes. An example of such is the Square Kilometer Array Observatory, which is an intergovernmental observatory, okay, established to build and operate the world's largest radio astronomy observatory. They are mostly located in South Africa and in Australia. So it's a picture of radio telescopes. Then we have microwave. For microwave, the telescopes we use to detect microwaves are microwave observatories or microwave telescopes. An example is the Planck Space Telescope, which was a project of the European Space Agency designed to study the cosmic microwave background radiation, which is afterglow after the Big Bang. Okay, this is the microwave. This is the Planck Space Telescope. Okay, although it has retired, it operated between 2009 to 2013. Then we have the optical spectrum. The telescope we use for optical spectrum is called optical telescope. An example, the most popular of them is the James Webb Space Telescope. Okay, I'm just focusing on the most popular ones, I mean, most sophisticated we have. So, and it is best known for combining high resolution imagery with powerful scientific instruments to study objects ranging from planets in the solar system to the most distant galaxies. It was designed by NASA and the European Space Agency and was launched in 1990 and is still in operation till today. So here are some of the epic images it was used to take very beautiful images. Okay. Then we have the telescope for observing ultraviolet radiations in the universe. We call it the UV telescopes. And one example is the Galaxy Evolution Explorer GALEX. It was a NASA orbiting space telescope designed to observe the universe in ultraviolet wavelength to measure the history of star formation. Okay, then we have X-rays. So the telescope we use for observing X-ray is the X-ray telescope or X-ray observatory. So it is the name. Our example is the Chandra X-ray Observatory, which is a NASA flagship space telescope for X-ray astronomy. It was designed to observe some of the hardest and the most energetic objects in the universe. It has been in operation since 1999. Then we have the last one, which is the gamma rays. So the telescope we use to detect gamma rays are gamma ray telescopes observatory. An example is the Fermi Gamma Ray Space Telescope, which is a NASA-led space observatory designed to study the universe's highest energy form form of light, which is gamma rays. It was launched in 2008. Now, if you also atmospheric uh, electromagnetic opacity. But before I go into this, if you look at everything I've just mentioned, you discover that all of them, almost 99%, are space telescopes. And you might ask, why? Why can't we have ground telescopes for gamma ray observatory, or ground telescope for X-ray, or for gamma UV rays, for microwaves? Why do we only have it in radio waves and maybe optical waves? I'm going to understand why in this section. So in this section, okay, so this is from altitude. This is the ground level, and this is the altitude 100%, and this is space. Okay, when these electromagnetic waves are incident to Earth, they are absorbed. So here you can see this is the section of the X-rays, gamma rays, and ultraviolet. They are absorbed. They don't reach the ground. They don't enter our atmosphere. They're absorbed in the upper atmosphere. But for visible light, they enters. Okay, visible light. I mean, the light coming from these objects, they enter our Earth, but to some degree they are stopped. Okay. Now, how about infrared? Infrared does not penetrate. Infrared does not penetrate. Okay, infrared does not penetrate. So that's why we have space telescope for them. But how about radio waves? See, we have radio waves. They can penetrate to the ground. They reach the ground. That's why we have this radio telescope here. You see that? The square kilometer observatory. So that's why we have them. Okay, so but for higher wavelength of radio waves, they are blocked by the atmosphere. Okay, so ground-based telescopes are mainly used for radio and visible spectrum or spectra, while most others, like the UV, X-ray, gamma rays observatories, require space telescope because Earth atmosphere absorb these high energy wavelengths. So now, advantages of electromagnetic waves. We have so many advantages, but I just listed three. Many physical processes. Okay, they are emitted by almost all astronomical objects, and they have provided the majority of the astronomical discoveries that we have made over the means since ancient history till today. Okay, so limitations. Some of the limitations are that the dust and gas absorb or scatter certain wavelength of the electromagnetic wavelength, especially visible and the ultraviolet light. Some wavelengths, such as ultraviolet, X rays, and gamma rays, are blocked by Earth's atmosphere and require space based observatories or telescopes. Light cannot always escape from extremely dense regions, limiting our view of some astronomical processes. So, thank you very much for paying attention to this lecture. In my next lecture, I'm going to be talking about the other three, uh, the other three cosmic messengers. So, thank you. You can post a question in the comment section.